some other examples for the aromatic, anti-aromatic, and non-aromatic. See, this of course has two electron pairs at oxygen, but only one participates. Remember, you got two pairs of electrons. Only one pair of electron participates, so that the total number of pi electrons will be 6. Therefore, it is aromatic. You need to be little careful. Okay. Similarly, in case of, so because only one pair of electron participates, the hybridization can be taken as sp2 even in this case also. 2 sigma bonds plus 1 lone pair. That is how we calculate the number of hybrid orbitals as well as the hybridization. Now the next one is, let us consider this. Okay. Even in this case also, see, you got two pairs of electrons. Only one pair participates in resonance. Right? So again, you will have, sp2 hybridized sulfur, and we'll be considering only 6 pi electrons. Therefore, even this also is aromatic. That is so special. Next, look at this interesting example. Now, this is called imidazole. The interesting part of this one is when you have, see here in this case, it actually participates in the reaction. This one, this pair participates in the reaction. Okay. So overall, the number of pi electrons, even in this case also, though you have a pair of electron and of course the pi bond, only one pair participates. So overall it will be again the same 6 pi electrons. Therefore, it is aromatic. Okay. Next. So look at this. See, in this case, if we consider this, we can say that it is anti-aromatic, isn't it? It has only 4 pi electrons. Okay. Now, if you consider this, so this is cyclopentadiene. When treated with the butyl lithium, it's an alkyl lithium. Lithium gets positive charge and butyl group gets negative charge. Just like the Grignard reagents, these are also organometallics. Now, in this case, consider, of course, you'll have 2 hydrogens here. This abstracts one of the hydrogens and the bonded pair goes towards carbon. Yes. Now, as a result, it becomes this. The negative charge, of course, you still have a hydrogen. The negative along with the Li plus. Now, this has 6 pi electrons. Okay. Plus, of course, the butane. Let us take this example. If this is the case, then nitrogen will have a positive charge. So because it has 1, 2, 3, and 4th electron. Only 4 electrons, it will have a positive charge. Now, this positively charged nitrogen is of sp3 type, right? Moreover, it has only 4 pi electrons, but still the nitrogen is sp3 hybridized, so therefore it doesn't have any vacant p orbital. If it were to be sp2, would have actually got a vacant p orbital, would have actually supported conjugation. But because it is sp3, you know, doesn't have vacant p orbital for conjugation. No conjugation, no planarity. So is non-aromatic. Remember, looking at the 4 pi electrons, you should not say that it is anti-aromatic. Okay, it's non-aromatic. Then the parent aromatic compound. Yes, this is of course our benzene. Benzene with 6 pi electrons is aromatic. Okay. Next. So this is pyridine. Even in this case also, because here you got a pi bond as well as a lone pair. The pi bond participates in resonance, not the lone pair. Okay. So because the pi bond participates in conjugation but not the lone pair, the total number of electrons here is taken only as a 6 pi. So is aromatic. The nitrogen here is of sp2 type with 3 sigma bonds. Now, if suppose this is taken into consideration, very interesting example, must have actually gone for aromaticity in GOC. See, this, of course, is benzene with the extra pi bond. This is the extra pi bond. But the point is, this extra pi bond is formed because of the poor overlapping. Okay. This, of course, can be given as pi bond formed due to weak or poor overlapping. Now, this overlapping will also be little bit interesting. Let me show you. So, even this pi bond is not considered to be a full-fledged pi bond. So, benzene is generally taken as aromatic. Okay. It's aromatic. Now, let me show you the arrangement of p orbitals. I mean the vacant p orbitals at the 6 carbon atoms of the benzene. Now look at the way they overlap. The upper portions and now the lower ones. This is a regular overlapping of the vacant p orbitals in lateral or sidewise manner. So this is how the cyclic delocalization of the pi electrons occurs. Now coming to the extra pi bond. Look at the way it is formed. This way. See, the p orbitals are perpendicular to the plane of the ring. Now, in this case, they overlap in this fashion, right? So this is not considered to be a proper pi bond and is formed because of the poor overlapping. It's a very important intermediate. Okay. Consider this one. Obviously, this is aromatic. It has 6 pi electrons, including that at including the lone pair, which is at nitrogen. Of course, the plus, the positive charge, will have a vacant p orbital. So look at this example. See, this is cycloheptatriene. Now look at this particular carbon. It is of sp3 type, right? So cycloheptatriene is non-aromatic because of the intervening sp3 carbon, which doesn't allow conjugation. No vacant p orbital. Therefore, no conjugation. Next. These are all the different examples only to get maximum clarity. Now, look at what happens when a positive charge is placed. This is an interesting compound. 1, 2, and this 3. Let me put a positive charge here. You know, this is called cycloheptatrienyl cation, famously known as propylium cation. Now, this carbon has become sp2 with a vacant p orbital. So, when you have a vacant p orbital, of course, you'll have proper conjugation, proper delocalization of the pi electrons. Though, I mean, here you got 6 pi electrons. Of course, even in this also you got 6 pi electrons, but because of problem with conjugation, because there is no proper delocalization, this one is non-aromatic, whereas this one is aromatic. This is very important. Propylium cation. Now, even that positive charge may be taken this way also. Let me put a boron. So even this boron, which is of sp2 type, will have a vacant p orbital. So even this also is aromatic. Now supposing if instead of positive charge, if we place a negative charge, here, then it will become anti-aromatic, right? It has 8 pi electrons, and there is conjugation. It's of course planar. Okay. Look at this. Now, when cycloheptatriene is treated with bromine, consider hydrogen here. Now, let us take this bromine in the form of Br plus and Br minus, or else simple Br Br. Let me take it this way. Okay. Now, if this way it is taken, we'll get a negative charge. So let us consider this way. H minus and Br minus goes up. That is how you can generate a positive charge. So H minus is what is actually going out now. You get a positive charge here with the Br minus plus the HBr what is being eliminated. So you get tropylium bromide. Okay. Let us go for Cyclo Octa Tetraene. Interesting one. So this is Cyclo Octa Tetraene, right? Now, as such, Cyclo Octa Tetraene, if at all is taken as this, I mean, this is of course planar, has 8 pi electrons. So we can say that it is anti-aromatic, right? But when the same cycloheptatriene, sorry, cyclooctatetraene is taken this way, See, when this also is cycloocta tetraene, but this is non-planar, it is a tub-shaped one, a non-planar one. You need to be little cautious. And it has to be checked whether they have given a clarity on whether it is a planar cycloocta tetraene with all sp2 carbons or a tub-shaped one. If it is a tub-shaped one, no doubt it is a non-aromatic because it is non-planar. Okay. So this is, of course, very important. Next. Now, supposing if it is given this way, take 2 potassium atoms and consider the possibility of resonance. So this is what you actually get. Very interesting. You get this? Means it is cycloocta tetraene, sorry, triene dianion. Yes, it is, of course, aromatic. It has got 10 pi electrons and there is perfect extended conjugation in this particular species. Look at this. These are the different types of species. See, when this is treated with SbF5, so when treated with SbF5, in this Sb is in +5 state. Now look at what happens when this is treated. Sb is in +5 in the thing what we have considered. Now the 2 fluoride ions have gone out and now the Sb, I mean antimony, is in +3 oxidation state. So from +5 it has become +3 by taking electrons from these areas, right? Earlier electrons were given and now the electrons are taken. But still, if you consider even this is aromatic, say it has 6 pi electrons. As far as the question is considered, they'll be giving only up to this, up to this. This is what you have to imagine. You have to say the answer. Okay.